the lab that I demoed last Wednesday, hand in for credit, and make sure that you do it just as if you're going to hand in the calculations only. Sorry. Hand in the calculations for experiment number 8? 10. Thank you. Experiment number 10. Calculations. And these are the 7 calculations. But I want you to do them, give them headings and everything. But here's the error. Over here, this is just a screenshot, but let's see. The percent error, okay. So actually, it's experimental. The word experimental and actual are the same. So experimental. So you'd get 0 there. Really, right? And experimental is equal to actual. Same thing. You can use those interchangeably, and I do. But instead of actual there, it needs to be theoretical. So experiment minus theoretical, final answer, divided by theoretical. Okay, so any questions about that? Yeah, it's a good opportunity to get lab credit and not do the lab. But what I showed you is kind of the equipment that you'll be using this Thursday. So that was good. All right. So another thing, remember when I had this slide? Actually, what I'd like to do, and I hope it's going to work out well, is I want to go back to part 4. So where it says on to part 5, that's correct. But where it says then to 6, no, we're gonna go back to 4. Okay, so kind of near the end of part 4, you should hopefully find this slide. Okay, that's on page. What page is that? Page 4. Okay, page 4 in that part. I know there's a lot of page 4s. Page 4 in part 4. So this is really, and maybe one of the reasons I delayed it when I've taught this other semesters is because this is really what you're going to do Wednesday. So if you want to put Wednesday's lab, or Thursday, excuse me, this is what you're going to do for Thursday's lab. If you want to put Thursday's lab, this is exactly what you're going to be doing. So we talked about, and actually we counted on the fact for the lab I demoed last Wednesday, this idea that you can have a couple of things happening within an isolated system, and they can share, basically swap energy. One will pick up energy, one will lose energy, and if your container or your system is isolated, the change in energy is 0 for your system. So we're going to look again at an isolated system. So the change in thermal energy that goes outside the barrier is 0. So there's no change in thermal energy. But we're going to look at a couple things happening in our cup or within our beaker, within our system. Okay. We've talked about chemical reactions that give off energy, exothermic chemical reactions, and chemical reactions that require energy, endothermic chemical reactions. And think of it this way. I'm introducing something called the Q of the reservoir. The Q of the reservoir basically is if something's giving up energy, okay, where is it giving it up to? If something's taking in energy, where is it taking in the energy to? So again, as long as your system of interest is isolated, we can say that what's ever happening with the solution is going to actually be your chemical reaction, is going to be absorbed or released from your reservoir. They're easier to show you than to do it. So do you guys have this as your next slide? Okay. But then you have a whole bunch of stuff over that. Okay, good. So what is an energy reservoir? Q of the reservoir. Like I said, that's kind of a place, a happy place where your chemical reaction gets its energy from or releases its energy into. Quite honestly, a lot of times it's just the chemical reaction itself. Okay, so again, we have exothermic reactions where with regard to the reservoir, okay, energy is going to be released from your reservoir, okay, an exothermic chemical reaction. And your solution is going to increase. one more line in there? Oh, that's okay, it's the other one. Alternatively, and this is like at the bottom of the page, it's at the top of my page, for an endothermic chemical reaction, of course, your reaction needs energy to proceed from reactants to products, and energy is going to be absorbed into the reservoir for your chemical reaction to occur. And in that case, your solution is going to be cooler. So again, an isolated system that has a couple things going on, endothermic or exothermic, we should be able to track the change in temperature of the solution or the liquid with regard to what's going on. Now finally here, probably instead of the word reservoir, I use the term chemical reaction. And of course my abbreviation for reaction is RXN. So basically, and we're going to look at some examples, you know, if this is my cup, my calorimeter, okay, I can have some sort of chemical reaction going on in here, chem RXN going on in there, and it will, okay, be endothermic or exothermic, and the juice, the liquid in there will either give up energy or absorb energy. But if it's isolated, then the change in thermal energy of the system, which is both those two things, the chemical reaction and kind of the juice that the chemical reaction is occurring in, the change in thermal energy of both of those added together is 0. So one will be positive and one will be negative. Like I said, it feels like it's easier to show it than explain it. All right. So let's do an example. Very wordy, very wordy. Okay, so let's draw a picture. Okay, it's a classic. So the other day when I did that copper experiment, I had my coffee cup calorimeter, and that's kind of what I'm going to draw here. Of course, it has a lid on it, and we're going to stick a temperature probe in it, just like we did before. Notice what this says is I'm going to put 0.500 grams of magnesium. Okay, and we have the chemical reaction down here, so I think I'm under my magnesium. 0.500 grams of magnesium is placed in my coffee cup, and my coffee cup also contains a liquid. That's actually going to be a great place to, it's going to be a great reservoir. And I have some information about the liquid. Notice my liquid has my other reactant, that's classic. So magnesium is reacting with HCl. So under my HCl, I've got the 100.0 milliliters, okay, and it is 1.00 molar, and it gives me a density. So under my HCl, I'm going to squeeze in green, the density of my HCl is 1.02 grams per milliliter. That's all my HCl. And then actually, just for kicks, I'm going to go ahead and say similar information there. I have 100 with 4 sig figs milliliters of 1.00 molar HCl, and density 1.02 grams per mil. All right, that's cool. Cup coffee. So we have a chemical reaction occurring between magnesium and hydrochloric acid in our cup that's isolated. And we're going to look at the temperature change. So down here, the next paragraph says, well, what's happening with regard to temperature in the cup? Okay, it says it starts out at 22.2 degrees Celsius, so that'd be my initial temperature. So I guess I'll pick green maybe. So T sub I, I'm going to go ahead and call that T sub I of the, let's see, T sub I of the I'll call it the solution. Yeah, I'll do that. T sub I of the solution is equal to 22.2 degrees Celsius. The final temperature, T sub F of the solution, is equal to 44.8 degrees Celsius. Exothermic. Perfect. All right. So now in italics it says calculate the enthalpy change. See, enthalpy, the symbol for enthalpy is H, right? So actually at the end of that equation, I'm going to go ahead and write question mark delta H, change in enthalpy. And I specifically want units for my delta H of, I'm running out of room. Units are going to be in kilojoules of energy per mole of magnesium. I love mole of magnesium. Okay, mole of magnesium specifically that reacted. Whew. Okay, so you get the idea. We have these two things reacting together. We know it's exothermic because we can see the change in temperature. The reaction's going to occur in the cup, and the solution's going to get hot. So basically, it's exothermic, giving it into the solution. So we're supposed to calculate the change in energy of the, which actually is going to be our Q sub RxN. Now notice down at the bottom it says, don't worry. It says, don't worry that some of your mass is actually going to be gone because of the gas. Some of it's going to leave because of hydrogen. Okay, and it says, assume that the resulting solution specific heat is the same as that of the solvent water. So in green up here, that's important. I'm going to say C sub P is 4.184. Remember I told you that, I think I told you to memorize that. Joules per gram degrees Celsius. So here in a minute, and I don't want to get too far ahead because we're going to do it on builds anyway, on slides. But can you see within this system, Q of the system, always look for what's going on? Well, we have the reaction. Q of the reaction must be exothermic because that water heated up. Plus, we have the water heating up, the water taking in the energy that's given up by the reaction. So I'll call that Q of the solution. Okay, does that make sense? So here's the deal. The water or HCl responding to the chemical reaction happening, actually we can get to that Q of the solution using Q of the solution is equal to M C sub P delta T, and that's totally how we're going to do it. By the way, that is equal to 0. So once we get to the Q of the solution, we're going to say, well, Q of the reaction is equal to negative Q of the solution, so we'll get the Q of the reaction. And the last thing we need to do, I'll show you how to do this, is basically make it into the enthalpy change per mole of magnesium that reacted. It's a mouthful. A mouthful. It gets one more thing, too. I forget this sometimes when I get to this problem, but you know one of the things we need to do, though? We need to see which one we're going to run out of first. So we got these two reactants. You're like, which one is the limited reactant? Because the limited reactant is going to basically drive the chemical reaction. And the limited reactant then is actually how we need to, say, normalize the heat that's released. So that's the next step. But that's kind of an overview of what we're going to do. Okay. So again, the solution got hot. We can come up with the amount, the change in thermal energy of the solution using the mass of the solution, the specific heat. They said use it the same as water. We got the delta T, no problemo. The mass of the solution, don't forget that you have to kind of add, in this case, the mass of the HCl plus the mass of the magnesium. Unfortunately, they didn't give you the mass of the HCl. They gave you the volume and the density of the HCl. So you're back to kind of something we did earlier. You're going for the mass. So the mass of the solution is the mass of the magnesium plus the mass of the HCl. Okay, we're going to use the same specific heat as water. So always read it carefully. For your lab that you're going to do on Thursday, I'm going to actually give you a different specific heat, slightly different specific heat of those solutions. The delta T is always final minus initial. So in this case, it's 44.8 minus 22.2 degrees Celsius, round according to decimals. Our delta T is 22.6 degrees Celsius. So on the next slide, I go ahead and show how we get to total mass. So the total mass is the mass of the magnesium plus the mass of the HCl. And again, we aren't given the mass of the HCl directly, but we're given volume and density. So we have 100.0 milliliters times 1.02 grams per 1 milliliter. That's the density. So we have 102 grams of solution. Notice if you want to be, just kind of keep watching those significant figures. We're multiplying here so we can allow 3 significant figures. So then we add that mass to the mass of the magnesium, which seems insignificant, doesn't it? So your calculator would display 102.5 if you take, if you take 102 plus 0.5, your calculator would display 102.5. But since we're adding, we need to round according to the fewest decimals, and the fewest decimals is that first term. So no decimals. So that's why it's really 103 grams of solution. Now, if you go ahead and use 102.5 grams of solution through your problem, that shouldn't make a difference, an issue. Actually, it's a better number as long as you round it right at the end. All right, so here we go. What's the change in thermal energy of the solution? M C sub P delta T. So the mass is the 103 grams. So here's the mass, 103 grams. Here's the specific heat, 4.184 joules per gram degree Celsius. And then here is your delta T, 22.6 degrees Celsius. Now, I'm kind of thinking that you don't have to, in this case, go all the way to kilojoules. Oh, yeah, you do. That's right. Eventually you will, because I know the problem said it wanted the delta H in kilojoules per mole of magnesium. Whew. All right. So taking it all the way to kilojoules, if we introduce 1 kilojoule over 1,000 joules, then notice our grams cancel, our degrees Celsius cancel, our joules cancel, and we're left with units of kilojoules. Okay, so that's how much energy was absorbed by the water, by the solution, by the HCl solution. So notice it is positive, which is what it should be, right? That water's absorbing it. All right. Well, okay. So what we're after is the enthalpy, the delta H of the reaction. The enthalpy, the delta H of the reaction. Now, here's one for you. Do you remember we said that as long as it's occurring at constant pressure, so it's not pressurized, you're not pulling a vacuum, actually these Q's that you're finding, okay, that is the change in enthalpy too. So we want the Q of the reaction. Only 2 things happening in your cup are you have the reaction giving up energy and you have the solution taking in energy. So there you go. Q of the reaction is equal to negative Q of the solution. And this is the sort of thing I'm looking for when I grade your papers and your assignments and your tests. I'm looking for this sort of logic. So Q of the reaction then is equal to what? Negative 9.74 kilojoules? Yes. And it was exothermic, so that makes sense. All right. So we could, let's see, how do we say this? You know, I said where delta H is the same as Q, you know, or if you have constant pressure. Well, it is, but that's not a good way to leave it, because that is specific for, if you look back at that diagram, that's specific for taking 0.5 gram of magnesium and reacting it with 100 milliliters of our 1 molar HCl. So we need to normalize it. It wants it per mole of magnesium. So basically, okay, so we're not done. This is my limited reactant problem. So which one are you going to run out of first? Well, I said the way I like to do it is I find the moles of, I find the have moles and the need moles. So in order to come up with the number of moles that I have of magnesium and HCl, this is what I need to do. So of course I use the molar mass of magnesium, 24.31 grams per mole, to get to the moles of magnesium. So this would be my have magnesium, 0.0206 moles of magnesium. And to get to the moles of the HCl, that's where I'm going to use the volume and molarity. So there was 100.0 milliliters of HCl. I need to get that to liters by the second term, 1 liter over 1,000 milliliters. And then the third term up there is the molarity, 1.00 moles HCl per 1 liter of solution. There's a lot of zeros and a lot of ones there. When the dust finally settles, you have 0.100 moles of HCl. So my next step is to take a ratio of have moles and compare it to a ratio from the equation, balanced equation of need moles. But these are the numbers I'm going to use for my have moles. And I think that there's, in this class, there's probably an assortment of ways people are finding the limited reactant. So from the balanced equation, the stoichiometric coefficient in front of the HCl is 2. So we need 2 moles. In front of the Mg, it's 1 for every 1 mole of magnesium. Okay? So we need 2 moles of HCl for every 1 mole of magnesium. If we go back the previous slide, what we have is 0.100 moles of HCl for every 0.0206 moles of magnesium. So if we solve that out, divide it out, what we have is 4.85 moles of HCl for every 1 mole of magnesium. So this is where I think I told you I kind of chant these back and forth. I say, well, we have 4.8 and we need 2. So we have more. We have more of what? Well, we have more of HCl. Okay, that's how I do it. So that must mean that HCl is in excess, which is probably what you kind of thought. HCl seems cheaper than magnesium. And it is in excess. So if HCl is in excess, then the one that we really care about is the magnesium, and it is limited supply. Phew. So now if you go back a few slides, when we got that amount of energy that was released for this specific scenario, basically we're going to take that energy and we're going to divide it by the mass of the magnesium. So actually, here we're taking that energy that was released, negative 9.74 kilojoules, and we're dividing it by the moles. You probably recognize that. I said mass, but if we divided it by the mass, then we'd have to use the molar mass of magnesium as the second term. But we already have the moles, so 0.0206 moles of magnesium in a half a gram. So we're ready to divide out and give it 3 significant figures. And that will be our enthalpy of the reaction per mole of magnesium. So the delta X sub RXN, the heat of reaction is negative 473 kilojoules per mole of magnesium, and that is your answer. I'm thinking for the homework, the 4 homework problems that you need to do, you don't have to identify the limited reactant, I think. On your test, I would not make you identify the limited reactant as part of this problem. The next time you guys are going to see limited reactants, have to identify what's in limited supply, will be on your final exam. Okay. So here's the problems that are due on Wednesday. And we are going to go on to on to part 6 here in a minute, but there won't be an assignment slide. So this is all that's due Wednesday. So let's take a quick peek at what these look like. These were quite colorful. So here's this one. So you see the reaction, chemical reaction of interest, the Fe2O3 and the Al reacting to form Al2O3 plus Fe. Let's see, when I did this, I had belts. Oh, okay. So notice they give you the amount of the two reactants in moles. Check it out. 1 mole of Fe2O3, 2 moles of aluminum. Is that not sweet? In red right there, I said you have an example where you basically have the right amount of each to totally react with each other. No need to identify what's there in limited supply. You know that because they match with the stoichiometric coefficients. Okay, so you're set. Stoichiometric amount is totally there. Notice the problem statement says that it's very exothermic, okay, negative 852 kilojoules of energy. I went ahead and kind of in the green and orange showed you combining the two reactants. We have an initial temperature of the stuff you start with of 25 degrees Celsius. It's an isolated system. They go ahead and they give you the specific heat of this blob. It's going to get warmer, it takes about 0.8 joules of energy to budget per gram of this stuff to budget its temperature 1 degree Celsius. That's just the specific heat of this. Now, also in the problem statement, it says that iron melts at a whopping 1,530 degrees Celsius. You're like, what does that have to do with anything? Well, iron is the product, okay, one of the two products. And it basically says, is this thing going to get hot enough to melt iron? All right. So, here we go. Let's see. Okay, so your system here, what's happening in that little black box there is basically you have your reactants coming together, it's highly exothermic, and your stuff's going to heat up. Okay, so Q of your reaction is equal to, plus Q of your stuff heating up is what's going on. Those two things are going on in your system. And of course, if it's isolated, it's equal to 0. All right, so yeah, we've been talking about this. So I said you don't have to pick any sort of, let's see, well, how do I say this? Oh, all right, okay. I don't think you need to, I think I have an extra step in here. I don't know. Let's see, I can, oh, darn. Okay. Yeah, I think all you need to do is this. Okay. Okay. So basically, no, I said that wrong. You do need to do this. So you have the enthalpy of a reaction, negative 852 kilojoules of energy. Remember, like we talked about Hess's law, or we talked about aside from Hess's law, that energy is associated with this specific balanced equation. So that says actually that amount of energy will be released if you react 1 mole of Fe2O3 to 2 moles of aluminum. So my hint here, all I said was you can use either your 1 mole of Fe2O3 or 2 moles of aluminum, and you can get the energy that's released. Basically, the energy of the reaction will be, whichever way you look at it, negative 852 kilojoules of energy, bottom line. And then you can go ahead and say that actually energy is going to be turned into heating up your products. Okay, so that negative 852 kilojoules of energy, that's actually positive, the Q here. Okay. So what's the mass of the products? Well, I don't know because they gave it to me in moles. So here in red I say you have to get to the mass of your reactants. Should be reactants. Products. You have to get to the mass of your products, I guess it would be products, from the moles produced and their molar mass. I guess it doesn't matter. The specific heat is 0.8. joules per gram degree Celsius. And the delta T, see here the delta T actually, you know your initial temperature is 25, but you don't know your final temperature. That's what you're trying to solve for. If your final temperature is greater than the melting point temperature, then it's going to melt. That's it. So it's kind of a maze. A maze. Okay, next one, a little more straightforward. This is a little more of what you're going to be doing Thursday. So you're taking a certain mass of potassium hydroxide. There's no chemical reaction. You're just dissolving it in water. But notice the water is going to heat up. Okay, so in this case, we don't really have a chemical reaction, but we kind of have a cue of dissolving. Okay, you could call that your cue of your reaction. Your water is going to heat up. We can track how much the water heats up. Okay, by taking the mass of actually the entire solution, which would be the water plus the KOH, potassium hydroxide, times the specific heat of the solution. I think they tell you go ahead and use the same specific heat as water. Change in temperature, you can get that from the initial and the final temperature. Then down here, once you have cube water, you can get the cube solution because they're equal in magnitude but opposite in sign. The change in enthalpy for the solution will be equal to the Q of the solution. We're normalizing it per mole of KOH. So we can, if we divide it by the mass of the KOH, then use the molar mass to get it in terms of energy per mole of KOH. And this one's similar. It is a chemical reaction, though. Oh, I think you do need to identify the limited reactant here. So notice I have step 1. Which one are you going to run out of first? Zinc or H? The H plus comes from your HCl. So you have to identify the limited reactant. Again, you mix those two. Looks like heat is evolved. The final temperature is higher than initial temperature. Okay, so you track the change in temperature. You relate that to the Q associated with the chemical reaction. And then you normalize it based upon a mole of zinc that reacted. Messy, messy, messy. Last one. Are you serious? Okay, this is a dissolving one again. And I think in my notes I say very similar to an earlier problem, problem number 21. All right, well, good thing there's only 4 of them. Okay. Good. On to just a bit of part 6. Standard molar enthalpy of formation. I love it when all in a title is what it is. Standard molar enthalpy of formation. What is it? Well, it is the formation, and actually we're going to have some practice at identifying. It's a chemical reaction. These are just different reactions. Okay, and they are the formation of 1 mole of compound, okay, from elements, okay, so those would be on the reactant side. And these elements need to be in their standard states, okay, so like, how do I say this? So are they going to be a solid? Are they going to be a liquid? Are they going to be gas? At standard conditions, okay? So standard conditions for thermodynamic problems, we said, are 25 degrees Celsius and 1 bar pressure, which is about 1 atmosphere. So for instance, the standard state of oxygen, okay? Standard state of oxygen at 25 degrees Celsius, 1 bar is a gas, okay? So standard molar enthalpies of formation, you know you have a chemical reaction that is the standard molar enthalpy of formation. If at the end of the chemical reaction it says delta H, superscript 0, subscript F. Little f means formation of. Standard molar enthalpy of formation. All right. What? Okay. So what does standard state? Like I said, well, basically, if you think of 25 degrees Celsius, which is room temperature, normal pressures, what is that thing going to be? Okay. Most of them are solids. Elements are solids. There are a few diatomic elements, and they will definitely be diatomic in the standard molar enthalpy of formation equations. Again, slightly different than standard conditions for gas law problems. For thermodynamic problems, it's 25 degrees Celsius and a pressure of 1 bar. Okay, so here's a good one for you. If somebody ever asks, what is the standard molar enthalpy of formation of an element, and that element is in its standard state, under standard conditions, it's 0. So that's helpful. So I don't know, yeah, you do have this. This actually, when we looked at the Hess's Law problem on Friday and we came up with the overall combustion of benzene, these were our puzzle pieces. These were the 3 little equations we used to get the overall equation of interest. And these actually are, how do I say this? These are delta H, standard molar enthalpies of formation. Okay, how do we know that? Well, we look at the reactants, carbon plus H2. Okay, so this right here is the standard molar enthalpy of formation of C6H6. This one right here, number 2, carbon and oxygen. This actually is the standard molar enthalpy of formation of CO2, exactly. This one right here, hydrogen and oxygen. This is the standard molar enthalpy of formation of water. Exactly. So on the next page is just a couple of equations, and they have the delta H's. And so we're going to say which one of these are truly representing a standard molar enthalpy of formation. So make sure that you look on, make sure you look on the product side when we look at these. Make sure it has to form only 1 mole on the product side. Okay, if it's not 1 mole, it doesn't count. It doesn't mean that you can't scale it back and make it standard molar enthalpy of formation. And then also notice that, so this would be on the product side. Then on the reactant side, make sure that the elements are in their standard state. So here we go. So this one, let's see, does it make the first criteria? I think so. Does it look like 1 mole is formed? Yep. 1 mole of CH4, that's cool. And does it seem like at 25 degrees Celsius that graphite or carbon, actually we talked about allotropes of carbon, and as it turns out graphite is the standard state for carbon under normal conditions. So that is right. Hydrogen should be a gas, that seems right. And it's diatomic, so that seems right. Perfect. So yes, this one is a standard molar enthalpy of formation of CH4. Smiley faces all around. Yes. So let's look at the next one. All right. Now notice we've got 1 mole being formed on the product side. That looks cool so far. Yes, 1 mole is being formed. Is it being formed from, let's see, lead? Is lead a solid? Yep. Is Cl2 diatomic? Yep. Is it a gas? Yep. Okay, so yep, this one passes too. This one is also standard molar enthalpy of formation of PbCl4. So we're 2 for 2. Yes. It works. I've got to have something that doesn't work here. All right. So how about this one? See, we are definitely forming 1 mole of PCl5, okay, but notice that PCl3 is not an element, right? So this one is not standard molar enthalpy of formation of PCl5. It fails. And then one more. All right. Well, our first check usually is to see that it's the formation of 1 mole. Nope, it is not the formation of 1 mole. Direct. But could we fix this? The formation of 1 mole? Yeah. We could like divide through by, or multiply by 1/2, and then we'd get 1 SR solid plus 1/2 O2 gas goes to form 1 mole of SRO solid. And actually that would have to be delta H SRO is 1/2 of negative 1,184 kilojoules. So we could fix it, but in and of itself it is not. All right, so that's how that goes. So then I just have kind of a series of tables. I don't have a whole lot to, we're not going to like belabor all these tables. But what I'd like to point out just a few things. So these are some standard molar enthalpies of formation of some assortment of stuff. Okay. So these are what you, I think, will find back in the back of Petrucci's textbook. Sometimes I change my textbooks, I don't change my slides, but I think I'm okay. Inorganic substances, by the way, are just generally things that have metals in them. Inorganic, okay? So here's some substances. Now I wanted to mention this because if you look back in your appendix, actually for each thing you're going to see 3 columns. So delta H sub F, that's the standard molar enthalpy of formation of that thing, okay, compound or element. Delta G sub F, that's Gibbs free energy of formation that we won't be talking about until, I think that's in general chemistry too. I love S. S is one of my favorite things because I can relate to it. Actually, it's entropy. Entropy, disorder, chaos. Oh. So that actually is the entropy associated with that. Okay, they're all thermodynamic characteristics. So again, I'm not going to go through all these. So they're alphabetical. Sometimes it's harder to find things than others. But you see what I mean about them. Okay, so those were inorganic things. I do want to mention, now if you see something that doesn't have a metal in it, it contains all nonmetals, it's probably organic. Okay, so it's going to be in a different table. Carbon and hydrogen are great at having kind of an assortment of compounds they form. Okay. The problem is, let's see if I have an example here. Oh, well, something to kind of look out for when you're dealing with standard molar enthalpies of formation. Notice we have benzene here. Okay, we have benzene in its gaseous state and benzene in its liquid state, 2 different values. Let's try to find another. Oh, yeah, that's not one. Okay, so then again, there's the standard molar enthalpy of formation, the Gibbs free energy of formation, and the entropy. More organic substances. So these get harder to kind of figure out where to find them. Okay, so that's great. This is where I want to start on Wednesday. And we'll come up with, we talked about standard molar enthalpy of formation. Standard molar enthalpy of formation.